Welcome to Orion. I'm David Fields, and the announcements are several. We got a lot of astrophotos. We're going to show them to you later in the meeting. I would like to tell them more about you, but our president's not here, and I was going to read from the newsletter where I put your vita in, but our editor said he would bring them. He just came in and he ran out with 8 copies. So can you tell us a bit about your background for our guests and for the people on the Zoom session?
Sure. I got my, I'm presently a postdoc at Oak Ridge National Lab. I work in the Neutron Symmetries division, or the Neutron Symmetries group of the physics division. I'm stationed up at S&S most of the time, but we're doing fundamental physics work. I got my Ph.D. last year at Indiana University, where my Ph.D. thesis was on measuring the neutron lifetime, and I'll actually work that into a little bit of this talk here. And then I guess before that, I got my undergrad at Cornell University, and I'm originally from New Orleans. So,
Good food. We're happy to help you.
All right, thank you. All right, cool. So I'm just gonna go ahead and get started. Is it all good? We got like cameras and everything on? Perfect. So when I give presentations, usually you want to start off with the important thing that people want to learn from their presentation. So my important fact is don't talk to reporters, because they're going to completely misinterpret what you're actually going to talk about because it sounds cool. So we are only sort of opening portals to the mirror world, and I will talk about what exactly we mean by that. So let's talk about just fundamental physics. When we talk about particle physics, we're going to be talking about the Standard Model. And the Standard Model is just a way that we use to calculate a bunch of things that we see in the universe. So all of the matter that we see is made up of some constituent particles. Those are quarks and leptons. The quarks are going to have a fractional baryon number. We're going to call them baryons. They have some fractional charge. They stick together and form composite stuff. That's why they're fractional. You have 3 quarks that bind together to form a proton or a neutron. Leptons are lighter. That's going to be your electrons. Those have what we call a lepton number of 1, and those just have an integer charge. They don't actually blob together with anything else. They don't combine into anything. They're just going to be free. And then we have all of the different interactions between them. We have gauge bosons. So if you're talking about the electromagnetic interaction, they're going to all have a photon that goes between them. If we're talking about the strong force, they're going to have gluons that go in between the different quarks and bind the quarks together. And if you are talking about the weak interaction, that's the force that controls radioactive decays. That's going to shift the different flavors of these quarks. So we're going to go from like a U to a D or something like that, or from an electron to a neutrino or something like that. Now, inside of the Standard Model, this actually sometimes gets a little bit confusing. We have antimatter. Antimatter is just you flip all the quantum numbers. So you take your quarks, you flip the charge, you flip the baryon number. It's still exactly the same thing. It's still going to have the same gauge bosons, but now all of your various different quantum numbers have changed. So you can still have antiprotons, you can still have antineutrons, and that's all within the Standard Model. And then antileptons are the same thing. You can have a positron, which is just a positively charged electron or something like that. So I guess the main takeaway of this introduction to particle physics is that we can use these quarks and antiquarks, and we can use these leptons and antileptons and combine those together to have some incredibly precise predictive power. You can go and just sit down and calculate out what the mass of different particles are. We used this to predict what the mass of the top quark or what the tau lepton were. You can use this to predict the masses of heavy gauge bosons, such as your W and Z. And back in 2012, we used this to figure out that, oh, the Higgs boson should be somewhere around here. And lo and behold, we went and found this. Now, I actually work in nuclear physics and not in particle physics. So Standard Model is wrong. And what I mean by that is the Standard Model doesn't actually touch anything regarding neutrino masses. We know that neutrinos have mass. You can measure it, or at least you can try to measure it, but we haven't seen that. And the standard model doesn't do anything with gravity. We just say, yeah, gravity, it's hard, it's out of here. If you go and look in the universe, you can go and look for how much mass we see in the universe. You can go and look at a galaxy, and it's going to rotate because it's a galaxy. It has some angular momentum, and the speed that it's rotating implies that there's a whole lot more mass in that galaxy than we see in the light. I have a question over here. I'm going to run over so people on Zoom can hear it.
Is it okay to interrupt?
Yeah, go for it.
Even though neutrino masses aren't part of the original standard model, can't we add them
retroactively? You can add them in retroactively, and that's going to come up with a couple of other implications later on. So yes, so there are various different ways that you can add them in. The standard model as written back in the 70s or whatever did not have neutrino masses.
Right. So when you said a couple of implications, that might not be desired?
That would lead to testable predictions, some of which we haven't necessarily seen yet. And I'll talk about one of those in a little bit more detail later on. Okay. So I was talking about dark matter as well. And we see that there's all this mass here. Could this be some sort of new particles? The weak interaction that I talked about, that one particular interaction, is actually left-handed. It only interacts on particles with a certain chirality. And that means that all the neutrinos that we have seen in the universe have all been left-handed. We have never seen a right-handed neutrino. When I'm talking about handedness, I'm just talking about the helicity, so the direction of the spin coupled to the direction that it's moving. All of the antineutrinos, because all of the quantum numbers have been flipped, all of those are going to be right-handed. So is this some sign that, hey, we need some more particles to restore parity to the universe? And then there's fine-tuning problems. I'm going to bring up one kind of big fine-tuning problem, which is that we exist. We're all matter, and we're not all antimatter, which, according to the standard model, is wrong. We can go and we should have an equal amount of matter and antimatter in the universe, but if you go and measure this, you can go and look, if you had a bunch of antimatter floating around somewhere, you would expect to see antiprotons hitting the atmosphere just because space is big and empty. So there should be some relic antiprotons just floating around out there. And you can go and look up in the sky. If you had a bunch of antimatter and matter somewhere, you would see some region of annihilation where the matter and antimatter meet. You would see a boundary in the sky, and we don't see that. You can go and calculate this out from the density from the cosmic microwave background, or you can go and calculate based on the abundances of elements in the universe. And all these things agree that the amount of matter in the universe compared to the amount of antimatter is somewhere at the 10 to the minus 10 level, which is small, but it's not zero. So where'd all of this go? Well, so back in the 70s, Sakharov, who was a Russian physicist, came up with a couple of conditions that we need to have a difference between matter and antimatter in the universe. So the first one, and this is a really big thing, is we need to have some process that violates baryon number. We need some way to have matter change into antimatter or matter change into something that's not matter, or vice versa. We also need to have the matter that we see requires that we have to have some favorite. We have to have matter favored over antimatter, so we need some sort of symmetry violations. We need to have charge symmetry violation or a combination of charge and parity violation just so that matter is favored over antimatter. And this is the only one of these conditions that we've actually experimentally found. Yes?
No, the initial conditions just didn't have more matter.
So again, if the initial conditions had more matter, you would see that in the cosmic microwave background. You would see some amount of anisotropy in the CMB that we just don't physically see. You would see it. Yeah, you would end up seeing. Oh God, I don't remember exactly what shape it would be, but you would see extra matter somewhere in the CMB spectrum.
So it's in the anisotropy.
Yeah.
and what's exerted?
Yeah, you would see a significantly higher anisotropy there. So, right, the CP violation is the only one of these conditions that we've actually seen. And then the other condition that Sakharov came up with was that we need some violation of thermal equilibrium so that once we have matter being produced, and once we have matter being produced favorably, it doesn't just fold back in on itself. Now, I'm going to focus on the first one for the rest of this talk. This is baryon number violation. It turns out in the standard model that baryon number and lepton number are not actually symmetries of it. The combination of the two is, but those two numbers in and of themselves, there's no reason to think that they have to be conserved. So you can use that prediction and say, okay, well, maybe you have protons decay. A proton is going to, which is a baryon number of 1, is going to turn into a lepton, a positron, plus some other stuff, and that's going to have a baryon number change of 1 and a lepton number change of 1. We've looked for that, we haven't seen any of this. Now, going in on the massive neutrinos thing, one of the potential implications of having a massive neutrino is that a neutrino could be its own antiparticle, in which case you would potentially have some mixing between your neutrino and your antineutrino state. And then you would expect to see what's called a neutrinoless double beta decay. You would have a nucleus that decays twice in a instant, and the neutrino would be its own antiparticle, so you wouldn't see any neutrinos there. What I'm going to talk more about is neutrons in this talk, which would have similar operators to these two other processes. It would have a similar operator for converting a proton into a positron, or you would have the same Majorana mechanism for converting a neutrino to its same antiparticle. And we haven't actually looked into this very much. Now I'm going to digress a little bit and talk a little bit about neutrons, because this is particle physics, and I don't necessarily know how much people have done particle physics here. So when I'm talking about neutrons, they're found in the nucleus of most atoms. They're slightly heavier than protons, and so we need them for stability. You can't have a bunch of protons just sit together inside of a nucleus. Eventually the Coulomb forces are going to cause everything to repel, and it's just not going to stick together. Neutron, as the name suggests, is neutral. It doesn't have a charge, but it does have a magnetic moment. It has a spin. It's a spin 1/2 particle, which means that it does couple to a magnetic field. And that means that it's a really useful tool for a lot of physics processes. And what they do a lot at the spallation neutron source, or at some of the neutron facilities in Oak Ridge, is they look for neutrons scattering off of materials, because they don't have that, they don't have any sort of electric interaction, so you can use this to actually probe the structure very well. And then we can use the neutron to probe strong and weak forces. Now, when you actually need neutrons to study in the lab, you have to produce a bunch of them. And that's a very energy-intensive process. So usually we produce them via nuclear fission or through spallation. Fission is just you have a heavy nucleus, say uranium or something, breaks apart, produces some lighter daughter nuclides, and then a bunch of neutrons. And then those neutrons can hit into a nucleus again and cause a chain reaction. And that produces a bunch of neutrons, and those are going to be very high energetic. The other thing you can do is you can take a particle accelerator, you can shoot a beam of protons, which are easy to accelerate, at some target, some solid target like mercury or tungsten, and if you put enough energy into it, it's just going to work like billiards. You're going to have the nucleus shatter, and into that, you're going to have a bunch of neutrons produced. All of these are going to be high energy, and when we actually do experiments with neutrons, we need to slow them down. If you go and look at your de Broglie wavelength for neutrons, a longer wavelength is just something that's easier to guide, easier to control. And also, if it's slower, if you're trying to put a bunch of neutrons inside of an experiment, you have more of them. You have a higher density. So for most of this talk, I'm going to be focusing on cold and ultra cold neutrons. Many of you might not have heard of ultra cold neutrons before. It turns out that you can go and do physics 101 stuff on a neutron, and you can go and say, all right, I've got a neutron. Let's raise it up into a gravitational field. How much energy does moving a neutron up a meter cost? And that's around 100 nanoelectron volts per meter. It's very tiny. You can do the same thing with the magnetic force. You can have a neutron, it's a spin-a-half particle, so it has a magnetic dipole moment. You can put that into a magnetic field and see how much force you get off of that. And that's around 60 nanoelectron volts. You could do the same thing quantum mechanically, have neutrons scattering off of a one-dimensional potential for, say, a certain material. And you can use that as a bottle trapping of neutrons. So if you wanted to do really, really low energy neutrons, you could combine all of these together and form a bottle of ultra-cold neutrons. So now I'm going to shift gears a little bit again. This is what I actually spend most of my time doing on the standard model. I work on neutron decay. And so a neutron is the simplest radioactive nucleus because it's just a neutron. You don't have to worry about any of the other structure functions. So a neutron is going to decay into a proton, electron, and antineutrino. And because it's the simplest possible decay, it's a really useful probe of the weak interaction. What's happening here is a down quark from the neutron is going to transition into the up quark of a proton. Now, if we wanted to probe this, there's two ways we can do this. Well, we can go and look at a couple of different experimental observables. We can go and look at the neutron lifetime, which is what my Ph.D. thesis was on. And then here at Oak Ridge, I'm working on the NAV experiment, which is looking at the momenta of the outgoing particles. Just really quickly, I'm going to talk about the NAV experiment because I think I'm contractually obligated to. We have a cold neutron beam. It passes through a giant magnet. We use that magnet to guide the decay products into one of two detectors, and then we can detect those. Now, it's a little bit difficult to figure out what the energy of these are. Electrons are 1,000 times more energetic than protons, are moving significantly faster than protons. So we actually reconstruct the energy based on how long it takes the proton to reach from the beam time up to the detector.
So what kind of magnetic field strength do you use?
Our peak magnetic field strength in here is around 4 Tesla. Okay. It depends. If I go back, yes, it's variable across here. We have a really low magnetic field here, and all of this weird stuff is to guide the decay particles so that they're moving basically parallel with the magnetic field. And then you can go and use these decay observables to get some physics properties. We can go and do relativistic kinematics, reconstruct the neutrino momentum based on what we've observed for the proton momentum and the electron energy. And so you can reconstruct some decay plot and use that to fit for some physics principles. I'm not going to go too much into that because this isn't the main focus of this talk. I'm going to go to the other measurement that you can do. You can go and measure the neutron lifetime. So for any particle that you want to measure, there's 2 different ways that you can measure the lifetime. I'm going to affectionately say you're either counting the living or you're counting the dead. So you can take your bottle and you can fill that up with some number of neutrons and see how many are left after some amount of time. And radioactive decay is going to be an exponential process. So you can do this for varying lengths of time. And as you continue to do this, you're going to fit out to an exponential curve. You put the same number of neutrons into your bottle, you see some number, and that's just going to fit along an exponential curve. You're not actually measuring the neutron lifetime here. You're measuring the lifetime of neutrons in your bottle, which is a subtle but very big difference because it means if you have some unaccounted for source of loss, that's going to bias your lifetime down. The other thing that you can do is you can say, well, I know my neutrons are going to decay into protons and electrons. So I can count the dead. I can count the decay products. If I have some flow of neutrons passing through a container and measure the number of protons or electrons coming off of that container, then if I absolutely measure those 2 rates, I should be able to extract the lifetime that way. It's a hard experiment because you have to calibrate 2 different detectors. Now you're not just detecting neutrons, you're detecting both neutrons and protons. And it turns out that these two methods disagree. There's a 4 sigma discrepancy between the neutrons measured with a beam and the neutrons measured with a bottle. And I'm going to touch a lot more on this later, but one of the fun things is that this can be explained if your neutrons are going to something that's not a proton or electron. Oops, I turned on the, okay. Shameless self-promotion, this is my PhD thesis work. It was the UCN tau experiment. It's a bottle type measurement of the neutron lifetime. We're just going to trap a bunch of neutrons inside of a gravitational field. And the cool thing about this is when I said that we're measuring the lifetime of neutrons in the bottle, you can go and measure different sources of losses for neutrons inside of the bottle. And here, the corrections that you would apply, the lifetimes of neutrons inside of our bottle, is somewhere around 2 or 3 weeks, which means that we don't have any sort of corrections less than our statistical uncertainties on the experiment. And so last year, we published a very precise measurement. We know the neutron lifetime is 0.288 seconds with a systematic uncertainty of around 0.2 seconds. Yes?
I'm sorry. So I'm curious about these loss mechanisms. Are some of them like you have in a mirrored plasma machine where you can get loss to a 90-degree momentum collision?
So in our case, a lot of the loss mechanisms are because we're using ultra-cold neutrons. And that means that if you have some heating mechanism, for example, we're trapping, in this particular trap, we have neutrons being held in Tesla-and-a-half field. So we can only hold neutrons that are of the order 50, 60 nanoelectron volts. So if you have some heating over the course of time, that's going to cause our neutrons to gain enough energy to get lost. The other thing that you can have is you can have impurities, and you can have neutrons scattering off of gases or something in there. And that's also going to be a loss mechanism.
And the neutron energy distribution is Maxwellian? Or?
In this particular case, we actually clean out our spectrum, so it's kind of exponential and then with a hard cutoff at the top. And that just means that we don't have some of the loss mechanisms that we would otherwise see.
Good.
How am I doing on time?
Doing great.
I'm doing great? Okay, cool. I'm going to gloss over some of this.
You gain them also, don't you?
Huh?
You gain neutrons too from cosmic rays.
Well, in this particular case, we don't get a lot of neutron gain. The cosmic rays would produce very high energy neutrons. And again, we can only trap low energy stuff. I'm going to skip through some of this stuff because I think, well, I'll go through and talk about this because it's always fun to talk about my PhD work. So how do we actually measure this? We're going to figure out how many neutrons are left after some amount of time. So we first fill up the trap, and we have to measure how many neutrons are in the trap, but that's a little bit hard because if you measure how many are in the trap, then we destroy them all, we count them all, there's nothing in the trap. So we have to extrapolate that based on looking at the energy spectrum here. And so we use various different monitoring detectors to figure out how many neutrons are in the trap. Then we change around our energy distribution. We get rid of all of the neutrons that wouldn't be trappable. We have a cleaning process where we just drop a sheet of polyethylene, which is going to just absorb or upscatter all of our neutrons away. And we lower that so that we actually have some cushion of trappable neutrons. Then we hold them in there for some amount of time. We usually would hold them for up to around an hour. After that point, statistics starts to get pretty bad. And then at the end, we have a detector that we lower into the trap, count how many are left, and of course, we have to subtract off some amount of background. The cool thing about this is that because we have such low energy neutrons, we can actually look at our systematics by using E equals mgh, physics 101 stuff, because the height that a neutron can rise into the trap is going to be dependent on how much energy it has. So you can lower your detector down halfway and count just the high energy neutrons and see what that population is and how that population has changed for various different holding times. And then you can lower it down and count all of your neutrons. I'm going to skip over this slide. Let's go back to the neutron lifetime discrepancy. So as I mentioned before, well, actually, Let me make first. All right, as I mentioned before, the beam lifetime, the lifetime measured based on decay products is around 10 seconds longer than the lifetime measured off of just trapping neutrons inside of a bottle for some length of time. And with our most precise measurement, we have no corrections that we need that are greater than the statistical uncertainty we have. So we're pretty confident in the bottle lifetime, this blue band down here. Now this can be explained if a % of your neutrons are going to go into some process that's not a proton or not an electron. Now this would be a baryon number violating term. See, I'm going to tie it all back to what I talked about at the beginning. Because we have a neutron that's going to not a neutron, you now have some baryon number violating process in here. Now, we can put energy limits on what the mass of this particle is and what the probability of transitioning on this particle is, just based on looking at nuclear decays that we know are possible or are not possible, and also based on looking at astrophysical constraints, stability of neutron stars of certain masses and things like that. That's going to put a limit on what the potential bands that we can look in. Now, let's go and look at a bunch of different problems and kill as many birds with one stone as we possibly can. We're going to try and attempt to explain dark matter, which dark matter might be some sort of new particles that we have floating around somewhere. Yes?
For the benefit of my astronomy class this year,
yeah.
Could you just briefly define dark matter?
Right, yes. When I'm talking about dark matter, I'm talking about matter that doesn't interact with light, which is kind of a tautological explanation. But when it's something that doesn't emit photons, or that's not electrically charged, or that doesn't produce gamma rays or anything like that. And we obviously can't see it because most of our astronomy stuff is going to be looking at photons. We're going to be looking at various different wavelengths of light, all the way from like radio telescopes up to gamma telescopes, but all of those are looking at photons. I think technically, depending on how you define it, something like a neutrino can be counted as a dark matter, although it's not enough to explain the dark matter that we see, because a neutrino is only interacting via the weak interaction. It doesn't interact with light. So it's wiffly waffly. I don't know. Some people kind of count it as dark matter. Some people kind of don't. But
maybe the neutrino would interact with dark matter in a way that...
A neutrino could interact with dark matter, potentially.
I thought people normally alluded to the rotation velocities of outer stars and galaxies.
Yes.
There was clearly a lot more matter in the inner region than could be explained by the luminous things.
Correct. Yes.
So that's the dark matter, whatever it is.
That's the dark matter. And that's one of the ways that we know that dark matter exists.
Yeah, so it interacts gravitationally, but you don't know of any other interactions.
Correct. Well, there are, I'll jump a little bit back on that. There are ways that you can have dark matter interact with itself. And there are limits as to how you can have dark matter interact with itself. But you can go and look at some nebula like the Bullet Cluster or something like that and put limits on how much of that is self-interacting. So I won't say that it's completely non-interacting with anything, because there are theories that propose self-interactions.
Some information about self-interactions.
There's some yeah. Gravitational is mainly how we see it, though. So we have this dark matter. We have this left-handed weak interaction. We have some process that we want to potentially violate baryon number, and we have this neutron lifetime discrepancy. So let's just throw everything at the wall, blob them all together, and copy-paste the standard model. We know the standard model really well because we can actually go and calculate everything, and it's pretty good at understanding what we have. But the one change we've made here is now we make our standard model right-handed. So the weak interaction is now right-handed instead of the normal left-handed. We would have the same other interactions. So we would have a dark photon, a dark gluon that would interact with other dark matter particles. And we would have the same composite particles. We would have a mirror photon or a mirror neutron or something along those lines. And then, because we're experimentalists, we want to be able to probe something, we can say, all right, now let's have our dark standard model, our mirror standard model, interact with our normal standard model through some sort of oscillations between neutral particles. In this case, I'm going to talk about the neutron. Yes?
Was the mirror model introduced as a theoretical idea shortly after the standard model started being?
Yeah, the original proposals for the mirror model come from Li and Yang or something, way back in the 50s or 60s or something. They just wanted to explain why the weak interaction was parity violating. And then it kind of sat on a shelf for a long time because people didn't really want to think that there's a whole bunch of weird stuff that we don't understand in the universe. And
as the decades kept on coming and new information kept on coming, it started to seem like maybe there was more value in it.
yeah, and there's definitely, it solves, you can have some fine-tuning problems that are also potentially solved by it as well. If you have you can put constraints on it doesn't have to be exactly identical between the two. You can have a slightly different Higgs mass or something, and that would lead to some changes in your fine-tuning and significantly reduce the fine-tuning that you'd see in the universe right now. So they told me that I was allowed to do a talk catered towards undergraduate physics majors. So I'm going to show the Schrodinger equation. If you don't know it, so I'm just going to talk about this Hamiltonian really quick. If you don't know what a Hamiltonian is, just think of this like energy. So the energy of a free neutron just floating around at the SNS or something, you have some terms that are due to mass and momentum. You have some terms that are due to the neutron interacting with stuff around. So you have a magnetic dipole, so you have interactions with magnetic fields. You have a neutron interacting with material. There's going to be some material potentials here. And then we know the neutron decays. We know the neutron can get absorbed into material. So there's going to be some loss mechanisms in here. We understand the mirror model pretty well because it's the same physics as the standard model. So we can write down the exact same Hamiltonian. We don't have to have exactly the same mass, or we're going to still have conservation momentum because that's just too crazy for us. But we can have a different mass because we can have a different Higgs, as I mentioned previously. We can say that there's some dark matter magnetic field. We're sitting inside of a giant gravitational well right now. We're standing on the Earth, which is in the solar system. You could have some mirror hydrogen or something that just is cycling around and forming a magnetic field. We could have some mirror material. Again, you have some capture of hydrogen gas nearby. Now, this is a quantum mechanical problem. It's generally going to be a question that you learn in sophomore or junior year of physics or something. You can write down a mixing Hamiltonian between these two, some mixing between your neutron and mirror neutron state, solve it out. I'm going to skip all the algebra and just say that the probability is going to go inversely proportional to the difference in energy between our two states. And so if we can change our energy states, and in the laboratory it's really easy to change a magnetic field, we can look for evidence of a mirror neutron state. We can look for evidence of a neutron going into the mirror neutron state, and changing around the magnetic field is going to allow us to fine-tune what, for example, the mass splitting between our neutron and mirror neutron state are, or what the presence of this potential mirror magnetic field or something along those lines would be. And so people went and searched for this as early as some of the proposals for it came out. The easiest way to measure it is to look for disappearance of neutrons inside of a trap. So when you're measuring the lifetime, you just put neutrons inside of a bottle and see if turning a magnetic field on versus turning a magnetic field off is going to give you a different lifetime. And so the first limits there were found, they're pretty stringent. You can say that the probability of transitioning, it's 1 every 500 seconds or something like that. But this only assumes that you have a perfectly degenerate case. You don't have any sort of energy difference between your neutron and mirror neutron state, and you don't have any mirror magnetic field. Your limits get significantly weaker if you say, well, there could be a mirror magnetic field with some angle to the Earth's magnetic field. You can go and search for this by just taking a repurposed experiment to look for the neutron electric dipole moment. They have very fine control over your magnetic fields, and you can tune them around and look for small gradients and look for small excesses in the loss rate there. And it actually turns out that for certain mirror magnetic field configurations, there are some controversial signals that you could have an excess loss rate. The other way that you can go and search for this is you can look at reappearance. You can do the double transition. You can have a neutron go into a mirror neutron and then go back. And the reason why this is useful is you can put an absorber in the way. Mirror neutron's not going to interact with the absorber. It's just going to pass straight through. But your neutrons, all of those are going to get absorbed. So on the other side, all you're going to see are going to be neutrons that had transitioned into the mirror neutron state. The advantage of this is that you get much higher intensity. You can just shoot a giant beam of neutrons from a spallation source or from a reactor at a target with a detector on the other side. And you don't have to worry about understanding your loss mechanisms very well like you would have in a bottle. And because you have a very long length of space to work with, you can get some very good control over your magnetic fields. But you need some long beam line, and now you're also looking at two really low probability things. So now, how would this actually work if you were going to look at the neutron lifetime? So when you're measuring a lifetime with the beam method, you have some beam of neutrons that's going to pass through some electrodes. And a fraction of those neutrons are going to decay into protons. You're measuring your neutrons at the other end of this electrode system. And so every once in a while, you're going to turn off the electrode, guide your protons out to an external detector with some magnetic field. But wait, neutrons interact magnetically. And that means that you now have some magnetic field sitting inside of this experiment that could be a compensation for a difference in energy between your neutron and your mirror neutron states. And you can go and calculate this, and that's what I've done here. So a neutron is going to be traveling from left to right on this plot. So you start off, so the blue line here is just going to be your magnetic field inside of the beam lifetime experiment, or the most precise of the beam lifetime experiments. The red line up here is the probability to be a neutron, and vice versa, to not be a mirror neutron. So when the neutron energy is exactly compensated for by your magnetic field, you're going to see a resonant change in the probability. And since you're measuring your neutrons and protons at different points, if you have a difference in the number of neutrons at the end and a difference in the number of neutrons in the middle, and those two numbers don't agree, you're going to shift your lifetime. And because this is a calculable problem, you can go through and simulate this. You can go and calculate this out for a bunch of different transition probabilities. You can go and look for different energy splittings between your neutron and mirror neutron state. You can go and look at different velocities. You can go and look at different couplings between the two states. So if you wanted to explain the neutron lifetime discrepancy, the combination of these is going to be this red line here on the plot in the middle. And so it's calculable. You would be able to see that 1% shift. Now let's talk about portals. This is the experiment that got us famous here at Oak Ridge. and we're going to shoot neutrons through a wall. We did this at MagRef. It's the magnetism reflectometer at the spallation neutron source. We have on one end a neutron detector, on the other end a neutron beam, and then in the middle we have a boron carbide absorber. We don't see anything. Neutrons are all going to get absorbed by our boron carbide. We turn on a magnetic field. If there's now a different energy splitting between our neutron and mirror neutron states. So some of them are going to have a probability to transition through and pass straight through our absorber and be seen in the detector on the other side. And again, we can go and calculate this out for all of the various different mixing parameters that we did for the neutron lifetime check that we did previously. And so once again, we have some magnetic field profile with an absorber in the middle and a probability to be a neutron and to not be your mirror neutron. And once again, we have resonant change in probability due to the magnetic field, but now we have an increased intensity of the neutrons on the other side just because we now have an absorber. It's going to block all of our neutrons, so we're only measuring one thing here. That's the neutrons after the magnet. So we can simulate this, and this is kind of what this looks like. We just did a parameter sweep over all of our region of interest for the difference in energies between the two and our different mixings between our neutron mirror neutron states. We can go and put limits on that based on what we saw experimentally. So does a transition between neutrons and mirror neutrons explain the lifetime discrepancy? No, doesn't. We didn't observe any counts above background. So this is our region where we were able to exclude in gray, and the red is the line that would explain the neutron lifetime discrepancy. So we did not see anything. Now, moving on, there are still reasons to look for neutrons and mirror neutrons. And you still have dark matter. You still want to restore parity to the universe. So you can keep searching, improve your limits even further. Recall that the energy of neutrons is going to have all these different terms in it, and we're looking for splitting in energy between the two. Well, our absorber has some sort of potential to it, and we just chose boron carbide because it was a great absorber. But that absorber has a Fermi potential that's at around 200 nanoelectron volts, which is right in the region of sensitivity. If you look at our plot here, this little chunk cut out in the middle is because we're just not very sensitive to stuff right around the Fermi potential of boron carbide. We're a lot more sensitive inside of our magnetic field. And so that means that we actually can switch to cadmium and get improvements on our limits that we can place. So we did this. We did this experiment at the SNS. We switched over to cadmium. We swapped over, did a couple of different magnetic fields. Previously, we'd just done 5 Tesla. Now we did 2.5 and 5 Tesla. Gives us more sensitivity. We understood what we were doing a little bit better. We can put additional shielding around our detector, get improvements down another 2 orders of magnitude. And so this is preliminary. It is being prepared by a paper that is on my laptop down there. We can go and get even more neutrons if we wanted. We can go all the way across Oak Ridge and go out to the high flux isotope reactor where you have a factor of 10,000 more neutrons. Over at GP Sands, we can get, again, good shielding. We can get good control over our material potentials, use cadmium everywhere. We can have a longer beam line so that we get better control over our magnetic field, put in magnets over there. And we did this experiment too. Turns out this was the first time that Hyper said, hey, let's just turn all the neutrons on. And so we actually irradiated everything. So we irradiated our detector and have some signal that we had to subtract out because we just saturated everything. So instead, we did a characterization study at Hyper. And actually got a subsequent beamline to do even more characterizations and to eliminate out some of the backgrounds that we would have due to activation of all of this stuff. And so hopefully in the future, we can actually get a dedicated run to put limits of a factor of 10,000 more on mirror neutrons at hyper. All right, let's go back to the standard model. Yes?
You irradiate yourself in the process?
We did not irradiate ourselves.
I got 10 milligrams in hyper once.
Ooh, that's fun. It popped up on my dosimeter. So I did have like the safety person say, hey, you actually got, you know, whatever the detectable amount is, and it was like exactly the detectable amount, but no more than that. And the detectable amount is orders of magnitude below what you're actually allowed to get at Oak Ridge. So they are very generous. But I definitely did have a discussion with my safety person of like, have you been doing experiments at hyper? All right, so in the standard model, we do have antineutrons. And you can do this very similar idea as neutrons to mirror neutrons. You can have neutrons going into antineutrons. And as before I mentioned, this is another form of baryon number violation that would be helpful, would be predicted by having a neutrinoless double beta decay, for example. This would be another avenue with which to search for the same mechanism, the same operators. The most precise measurements that we have of neutrons going into antineutrons comes from stability of nuclei. If you have like an oxygen nucleus, it's not going to decay because it's not going to spontaneously transition into antineutron. And you can calculate what that is. You can go and look inside of a big neutrino detector or something like that and look for a bunch of pions that would appear isotropically. We call it a pion star. And you would just see a bunch of pions that are going to be produced all at the same time in the same spot. You can put limits on that, and they're pretty good. You could do the same thing with a free neutron beam. You just have a beam of neutrons passing through, and then at the end you have some target that would produce a bunch of these pion stars and detect any sorts of antineutrons. And this result, the most recent neutron antineutron oscillation, so entirely in the standard model, was done in '94. Now, this slide's dedicated to the people in the back of the room who weren't alive for 1994. So a little bit of history. The last time that this experiment was done was Friends season 1, and O.J. Simpson was still an actor. Nirvana was still recording music. There were some improvements in computing. The PlayStation 1 came out, Python version 1 came out, and Netscape Navigator came out. So, you know, we have a lot of great scientific progress happening in 1994. It's a little bit time for an upgrade. So we could actually upgrade this just based on the fact that almost 30 years have passed. We can get a significantly better experiment with using modern technology. You can go and buy neutron reflectors off the shelf that are way better than what they had in the 90s. You can go and buy computers off the shelf that are way better than what they had in the 90s. You can go and get vacuum equipment off the shelf that's way better than what they had in the 90s. And so on and so forth. You just get way better everything for cheaper because it's 30 years have passed. And so we're actually dedicating some beam time to doing this at the European Spallation Source, and they're building a new beam line for exactly this purpose, exactly this search. So wait, I was talking about mirror neutrons. What about antineutrons? Well, you could combine the two. You could have a neutron go into a mirror neutron, into an antineutron, and that has 6 orders of magnitude different limits. I went and did the math earlier today. The probability of one neutron transitioning, if you just picked a neutron, this characteristic time is something around now to 10,000 BC for antineutrons, and it's about 10 minutes ago for mirror neutrons. So if you have that transition happening, it's going to be a lot more probable if you could have a dark matter intermediary in this otherwise standard model process. So you could do a search for this and find a very, very competitive limit on neutrons into dark matter stuff into antineutrons. And so we're actually planning on doing this at Oak Ridge and in conjunction with the European Spallation Source. You can go and put a barrier in between your neutron beam and just block all of the neutrons and use that for calibration of the eventual neutron antineutron detector. All right, so I will end here and I will thank the collaborators. This was a big collaborative experiment. We have a lot of collaborators from many different institutions. So thank you.
I got a naive question.
Yes.
About these transitions from neutrino to antineutrino. I'm missing the boat somewhere. What about conservation of angular momentum?
So the idea there is that a neutrino is its own antiparticle. And for conservation of angular momentum, the spin of the particle can still be, I have to think about this a little bit. Yeah, I haven't thought about neutrinoless double beta decay in a while. So I think there is some mechanism by which, I guess you have a spin conserved. I'd have to look it up, I'm sorry.
Okay.
It's really interesting to go off of this. You know, you start out with these interesting observations that neutrons in the bottle have a different lifetime from neutrons in the beam. And really, you've got another data point too, between those two, I think. That is the neutrons stuck in an atom usually last forever. So it seems like maybe it's proximity to other things that makes the difference.
Right. So neutrons that would be stuck in an atom are going to have a very high Fermi potential. So the Hamiltonian between neutrons stuck in the atom, they just have a bunch of energy from the nuclear binding energy. And so that would suppress the probability of transitions to somewhere around where you would see that 10 to the 8 seconds that you'd see for antineutrons as well.
But you have the same effect if you start packing them into your magnetic bottle. So the bottle is really full and they start interacting more.
We haven't gotten densities high enough to be able to do that yet. That would be a really fun experiment, and I've thought about how to do like a neutron collider. It's a hard problem because it's hard to get high enough densities.
2 hyphers.
2 hyphers with like a neutron storage ring in between or something. I've thought about it as a kind of joke proposal for the second target station for the SNS, just shoot 2 beamlines at each other. But you need to do a little bit of extra work to get neutrons hitting neutrons and trapped off of other neutrons.
That's great. That's great. Thanks again.